Okay, we're going to be talking about alternating series next. So first, let's make sure we can identify what an alternating series is. Let's look at this first series. If we plug in n equals 1 and write this series out, we can see that the first term is negative 1 squared, which is a positive 1, times 1 over 1 is 1. And then the next term is negative 1 to the third power, so it's going to be a negative number, and it's going to be 1/2. And then we'd get positive again, 1/3, and then it'd be a negative 1/4, etc. So we would consider this an alternating series since the sign is alternating from positive to negative to positive to negative, etc. Let's look at the next one. If we set n equal to be 1, we get 1. If we plug in n to be 2, we get actually a negative 1. And then it's going to alternate to 3/4, and then a negative 1/2, positive 5/16, a negative 3/16, etc. So again, we would classify this as an alternating series since the sign changes from positive to negative to positive negative. If in any of these examples I'm going too fast, feel free to pause the video and double check my computations. Okay, in this last one, if we set n equal to be 1, we get 1 over 1 times sine of 2 minus 1 is 1. So sine of 1/2. So sine of 1/2 pi is sine of pi over 2, which is equal to 1. Since again, I just drew this unit circle to show you that the y coordinate at pi halves is 1. So the upshot is we get 1. Likewise, we can substitute n equals 2, and again, you can feel free to double check these values. We get negative 1/2, then a positive 1/3, a negative 1/4, and a positive 1/5, etc. So in fact, this is the same series in a different format as the first one. So all of these are alternating series since they alternate in sign. It doesn't have to go from positive to positive again. It can start negative and then go to positive, or really any pattern of alternating back and forth within the signs. Okay, now we're just going to look at some patterns with with alternating series. We're looking at the absolute value of the nth plus 1 term compared to the nth term. So in this first case, since n is 1, this would be a2 compared to a1. In the next case, this would be a3 compared to a2, and then a4 compared to a3. So a sub n plus 1 is always saying the n plus first term. So it's the term after a sub n. So in general, we're looking at some term compared to the term right before it. Okay, so I'm going to fill in this chart. So when we compare these values in general, we see that the n plus first term is always less than or equal to the nth term. And then we're also asked to evaluate the limit as n goes to infinity of a sub n. So again, the a sub n is your absolute value of the nth term, so that in this case is just the limit as n goes to infinity of 1 over n, which is of course 0. We can repeat this process for the second example. We again see that the n plus first term is always less than or equal to the nth term. So now we evaluate the limit of as n goes to infinity of a sub n, so that's going to be taking the limit as n goes to infinity of, we need to get rid of that negative term, so it's just going to be 2 to the n minus 1. So in some sense we're factoring out the negative 1 to the n minus 1 power, and we're removing it since we're looking at just the absolute value. So let's evaluate this limit. If we plug in infinity in some sense, that we get infinity over infinity, so we can apply L'Hopital's rule, and we see that again this limit is 0. This third example is exactly the same as part A, as we saw by actually writing out the sequence. So we're going to get the limit to be 0, and again we're going to have that the nth plus first term is going to be less than the nth. Now all three of these alternating series are convergent. So what are some general statements we can conclude from these questions? And basically this is what the alternating series is. Alternating series test is. So the alternating series test says if we let a sub n be the positive portion of the alternating series, so in other words take the absolute value, then the alternating series, so we have some portion of it that will make the signs alternate, but then here's the a sub n part, and again it doesn't matter if it's alternating from negative to positive or positive to negative. So what the test says is that these alternating series will converge if we satisfy both of these criteria. So one is that the limit as n goes to infinity of the positive terms goes to 0, and also that the nth plus first term is always less than or equal to the nth term. So this is really just saying that the terms are getting smaller. So, and this always has to be true for at least some, it says for all n, but really if it's not true for one or two terms in the beginning, that's okay, as long as at some point it's always true. So in a lot of senses, the alternating series test feels like somewhat of a weak test, since really this limit as a sub n goes to 0 part, that's really just the nth term test, which we already talked about in class as being a strictly divergence test. If you don't know what I mean by that, please look that up. So the nth term test is a test we've already studied. It says if the limit as n goes to infinity is 0, we are normally not allowed to conclude anything. This is part of the alternating series test, so it seems like a weak test. However, we can further classify convergent alternating series as either absolutely convergent or conditionally convergent. So for a alternating series to be absolutely convergent, it means that the series passes the alternating series test, so in other words it is convergent, but in addition to that, if we were to remove the sign from the series, that the all terms positive series, that the absolute value of the series is also convergent. So that will require a new test. You have to do some other test we've already looked at, maybe a comparison test, maybe it's a p-series, maybe an integral test, whatever. So notice that, for example, the alternating series, -1 to the n times 1 over 2 to the n minus 1, this converges because it would pass the alternating series test, but also it converges absolutely, since if we were to remove the sign, 1 over 2 to the n minus 1 is just geometric with a ratio of 1/2, so we know it converges. So this series back here, this alternating series, is an absolutely convergent series. If the series converges, in other words, it passes the alternating series tests, those two conditions, but if we were to remove the negative from the problem, so like in this case, if we remove the negative, we're left with the 1 over n, which we know is divergent, then we say that this series is conditionally convergent. So both of these are convergent in the sense that they pass the alternating series test, but if you remove the sign, this first example still converges, the second example no longer converges. So that's the difference between absolutely convergent and conditionally convergent. Absolute convergence is important for two reasons. We have effective convergence tests for series where the terms are positive, so this is good that we can actually check this. And it's important to note that if a series converges absolutely, then it converges. So every time we have an alternating series, we will first use the alternating series test to check to see if it converges or diverges. If it diverges, we're done. If it converges, then we have to test further. We have to check the series without the sign and check to see if it's conditionally convergent or absolutely convergent. Let's look at some examples. So note in this case that a sub n is just 1 over the natural log of n. That's because, again, we're looking at a sub n is always the absolute value of this term. So we need to check two conditions. We need to check to see if the limit as n goes to infinity of a sub n equals 0, and also if the n plus first term is less than or equal to the nth term. So if we take the limit, we see it is 0, so that is satisfied. And if we compare what happens if we plug n plus 1 into the formula compared to n, we see that over here the denominator is bigger, which makes the series in fact smaller. So yes, in fact, this is true. So this converges. So now we have to check to see if it's conditional or absolute convergence. This means we have to check to see if this new series, if we remove the negative sign, if this new series converges or diverges. So think for a moment about how you'd actually check to see if this converges or diverges. So we can do a comparison. If we compare to 1 over n, which is a divergent p-series test, we can actually do a direct comparison. Since all of the terms, so the natural log of n, this is going to make the numbers smaller denominators, which will make the entire terms bigger. So by the direct comparison test, this series diverges. This tells us that our original series converges conditionally. Let's try another example. So a sub n is n plus 1 over the natural log of n plus 1. We want to check our two conditions. When we evaluate our limit, we see we get something of indeterminate form, so we can apply L'Hopital's rule. Note here that we are going to flip and multiply. This expression is really just n plus 1. So as n goes to infinity, this goes off to infinity, which is clearly not 0. Once one of these is not met, we know that it can't satisfy both. So by the alternating series test, this series diverges. And we don't have to check now for conditional or absolute convergence because it diverges. To see what a sub n is in this next example, we have to actually think about what the terms are. So picture cosine. This is admittedly not my best picture, but we see that cosine of 1 pi, which is when n equals 1, that's going to be down at -1. So this is the series -1, plus when a cosine of 2 pi is +1, 3 pi it's going to be going back to -1. So this is just the alternating series, +1, -1, +1, -1, like that. So a sub n has to be the absolute value of these terms, so a sub n is just 1. So we quickly see that this series is going to diverge, since the limit as n goes to infinity of 1 is 1, which is of course not 0. So this series diverges. Let's try the next example. A sub n is 1 over n to the 3/2. Let's check our two conditions. So is the limit as n goes to infinity of this expression equal to 0? And hopefully you would say yes. Likewise, if I make my denominator bigger, that will make my term smaller, so this is also true. So this converges. Now we check to see if it's absolutely or conditionally convergent, so we look at the series without the alternating sign and evaluate what happens. This new series converges by the p-series test, thus our original series converges absolutely. Okay, we have two more examples. I would encourage you to pause the video and try these on your own and then check your answers. Okay, checking our two conditions. The first one clearly goes to 0 since the denominator gets very large. And again over here, this is my denominator is larger here, which makes my term smaller, so this does pass both criteria for the alternating series test and does converge. So we now have to check if it's conditionally or absolutely convergent, which means we need to check if this series converges or diverges. This one may not be as obvious, but we're going to do a comparison. We're going to compare to 1 over 2 to the n. Remember, in this fraction, the denominator is 2n plus 1 times 2n times 2n minus 1, and we keep multiplying by smaller and smaller integer values until we get to 1. That's going to be a much larger denominator than if we just multiply 2 times itself several times, or n many times. So since this one has denominators that are larger, it's going to be always smaller. Now this series here is a convergent geometric series since r is 1/2. So we have terms that are always smaller than a convergent geometric series, so this series converges. This tells us that our original alternating series converges absolutely. Okay, for our last example, again, maybe you want to try this one on your own. So we check our two criteria. We notice in this first example, in fact, the limit is equal to 1, so this will not equal 0. So we don't have to check our second condition, although just looking at the first few terms, we see that this one is also not true. So this series diverges. So to summarize, for alternating series, you have to first check the alternating series test to see if the series converges or diverges. If it diverges, you're done. If it converges, you then have to test the series without the alternating sign part. Check to see if that series converges or diverges. That will tell you if your original series absolutely converges or conditionally converges. There's a lot of steps, but they're the same every time.